We will
Save money with Snapshot ProView. Instant savings on your commercial auto insurance and vehicle.
pull and serve the elements with the highest priorities first and work our way to elements with lower priority. So yeah, that's a priority queue. If you would like a copy of this code, I'll post this to the comment section down below. And well, yeah, those are priority queues in computer science. Hey, what's going on, everybody? It's your bro. Hope you're doing well. In this video, we're going to discuss linked lists and computer science. So sit back, relax, and enjoy the show. Now, before we dive straight into linked lists, we're going to take a closer examination of arrays and array lists. We will see what disadvantages that these data structures have, where linked lists excel at, so we'll compare and contrast the differences between the two. With what we understand with arrays and array lists, these data structures store elements in contiguous memory locations. In this demonstration, I'm storing letters of the alphabet. Suppose that the first element of my array has a memory address of 123 Fake Street. Obviously, these are not real memory addresses, but this is how I like to think about things. If this was a memory address, then the next element in my array may have an address of 125 Fake Street, then 127 Fake Street, 129 Fake Street, and then you just continue on in that pattern. Now, arrays are fantastic at randomly accessing elements because they have an index, but they're not so great at inserting or deleting elements, especially when those elements are closer to the beginning of the array. Here's an example. Suppose I need to insert a new element at index 3. Since this element is already occupied with a value, I would need to shift my elements to the right in order to accommodate room for this new element. So the process of shifting is cumbersome. But once this element is empty, then I can insert a new value. So it's not that big of a deal if I have a small data set, but imagine if I had 1 million elements. I will need to shift my data up to that many times, depending on the location of the insertion. And the same concept applies with deletion as well. We would shift our elements to the left to close the gap. You're probably thinking, dude, why are you talking about arrays in a video about linked lists? Well, where arrays have difficulty inserting and deleting, linked lists actually have the advantage. Here's a representation of a linked list. A linked list is made up of a long chain of nodes. Each node contains two parts: some data that we need to store, and an address to the next node in line, also referred to as a pointer. Linked lists do not have an index the same way that arrays do, but each node contains an address to where the next node is located. So these nodes are non-contiguous. They can really be anywhere within your computer's memory. If our initial node has a memory address of 123 Fake Street, like our array example, then the next node in our linked list could have a memory address of maybe 101 Help Boulevard, and another could be 404 Nowhere Lane, then 666 Crime Circle. Each node knows where the next node resides. I imagine this as if we're following a scavenger hunt or a series of clues to find the end of the linked list, the tail. Each node has an address, a clue as to where the next node is. We begin at the head and work our way towards the tail, following each clue, each memory address found in each node. Then we know when we reach the end of our linked list when we check that address, our pointer, and it has a value of null. That means we're at the tail, we're at the end of our linked list. Inserting a node is easy in a linked list. There's no shifting of elements involved. Wherever we need to place a new node, we take the address stored in the previous node and assign the address of our new node with the address from the previous node so that our new node is pointing to the next node in line. Then we can take and replace the address in the previous node with an address that points to our new node. It's as simple as that, and we're completing our chain simply by inserting a node at a given location. There's only a few steps involved, no shifting of elements required. Deleting nodes are easy too. Wherever we need to delete a node, we have the previous node point instead to the next node in line. Again, no shifting of elements is necessary. Now, this is where linked lists tend to be inferior to arrays. They are bad at searching. We can randomly access an element of an array because we have an index. With a linked list, that is not the case. To locate an element, we need to begin at that would take linear time, but a doubly linked list requires even more memory to store addresses in each node, not just one, which is the case with a singly linked list. One address for the next node and another for the previous node in our chain. The benefit of a doubly linked list is that we can traverse our doubly linked list from head to tail or from tail to head in reverse. Each node knows where the next and previous node is, but the downside is that a doubly is even more memory than a singly linked list. So how about we create a linked list in real life now? Let's do it. All right, ladies and gentlemen, with all of that out of the way, let's create a linked list. Linked list List the data type of the objects we'll be storing within this linked list, just strings because they're easy, and I will name this linked list linked list. Linked list equals new linked list. And list type again, we are storing strings, adding a linked list. Now, if I was to take my cursor and hover over my linked list declaration, there's a note here that says this is a doubly linked list. Each node knows where the previous and next nodes are. Now, if we head to the linked list class itself, there's a few things I need to mention here. Our linked list stores the memory location of our first and last nodes. These are effectively the head and the tail of our linked list. And there's also an inner class named node. Each node knows the memory address of the next and previous nodes within this linked list. Now, taking a look at our linked list class definition, our linked list class implements the deck interface. And a deck is more or less a double-ended queue. So with the deck interface, we implement methods. So here's just a few of them. So we can add to the head, add to the tail, remove the head, remove the tail, peek at the head, peek at the tail. Some will throw exceptions, some will return a special value. So you can use any combination of these really. And not only do we have these 12 methods, but we can treat our linked list as either a stack or a queue. We can push, we can pop, we can pull, and we can offer. So just to demonstrate, let's first treat our linked list as a stack. So linked lists do have a push method as well, if we need to push an element onto our linked list as if it were a stack. So let's push the letter A, and then I will display my linked list with a printline statement. System.out.println, linked list, and of course we have the letter A. So let's push another letter onto our stack. What about B? So at the bottom of our linked list, we have A, and then on top, we have B. Let's add a couple more letters. Let's represent a typical grading scale. We have C, D, and F. A, D, F. Notice that I'm intentionally leaving out E. We're going to insert that later. So within our linked list that's behaving as a stack, we have F on top, then D, C, B, and A. So we also have access to a pop method as well, linked list dot pop, and this will pop the top of my linked list. So F should no longer be here. It's D, C, B, and A. So we can treat a linked list as a stack. We can also treat it as a queue as well. And just to save some time, I'm going to copy these lines of code. To add an element to a queue, we do not use push, we use offer. So linked list dot offer. And we will keep the order. So I'm not going to pop it quite yet. So we have A, B, C, D, F. A is at the head, F is at the tail. And to remove the head of our queue, we do not use pop, we use pull. And A is no longer in here. We have B, C, D, F. So you can use a linked list to mimic a stack or a queue. Before we move on to the next section, I'm going to get grading scales A, B, C, D, F. Where linked lists are really good is the insertion and deletion of nodes. Let's say for this example, I need to add a node between D and F that contains the letter E. So that's really easy to do with a linked list. We would type the name of our linked list, dot add, list and index, like 4, and our E. And then to remove a node, we would type the name of our linked list, dot remove, then list the object, E. So E should no longer be within my linked list. So where linked lists tend to have an advantage over arrays and array lists is the insertion and deletion of nodes. However, there's one catch to this. With a linked list, we still need to traverse the entire linked list to find where we need to go. Unlike with arrays and array lists, there's no random access to a linked list. Searching for an element is fairly straightforward too. So within use the index of method of a linked list. Linked list dot index of, let's look for F. So that would be at index 4. And before we wrap things up here, here's a few methods related to linked lists that you might be interested in. We can peek at the head or the tail node of our linked list. So within a printline statement, I'm going to print linked list dot and then use the peek first method. So the first node within my linked list contains the letter A. So we can peek last as well. Linked list dot peek last. And the last node of my linked list contains the letter F. We can add new nodes at the head or the tail of our linked list by using the add first method for the head. So maybe I need to add maybe 0 because I don't really know what comes before A in the alphabet. So 0 would be a good bet, I guess. Or we could add to the tail by using add last. And after F comes G. And we now have G at the tail of our linked list. We can remove first and remove last. You can also string first equals linked list dot remove first. Then to remove the last node, we could just use remove last then. And let's store this within a different variable, remove last. So yeah, those are a few useful methods related to linked lists. In conclusion, everybody, a linked list is a data structure that stores a series of nodes. Each node contains two parts, some data and an address. Nodes are stored in non-consecutive memory locations. Each node can be really anywhere within your computer's memory, and elements are linked via these pointers. They contain an address for where the next node is. We've discussed two varieties of linked lists, a singly linked list as well as a doubly linked list. With a singly linked list, each node is made up of two parts, some data and an address. To traverse a singly linked list, we would begin at the head node and use the address as a sort of clue to find where the next node is located within our computer's memory. With a doubly linked list, each node is made up of three parts, for the next node and another address for the previous node, and it behaves the same way. And to traverse a doubly linked list, we could begin at the head and work our way towards the tail, or we could begin at the tail and work our way towards the head, depending on which way is closer to where we need to be within our linked list. What are some of the advantages of a linked list? One, they're a dynamic data structure. They can allocate needed memory while our program is currently running. Two, insertion and deletion of nodes is really easy. If you're familiar with big O notation, this would be in constant time. There's only a few steps regardless of the size of our data set. And three, there is no to low memory waste. What are one, there is greater memory usage because we have to store an additional pointer. Each node also stores the address for where the next node is located. And even more so with a doubly linked list, this will use a lot more memory because we need two addresses for each node. Now, two, there's no random access of elements within a linked list. To find an element, we need to begin at one